Hello and welcome to my lab. Today I have for you an even newer communication analyzer, this time made by Agilent, basically the successor to the test equipment branch of HP. So I'm going to do the same thing. I'll tear it apart and see what's inside. Let's see what happens if we turn it on. I hear a few small high-pitched fans. There's something on there, processor 400 MHz, and you very clearly see the LCD screen has been smashed. It's staying stuck here, so my guess is that the battery for the memory is empty and it asks an F1 to continue, something like that. Of course I don't have a proper keyboard or even a proper screen at the moment, so it's hard to press continue. I hooked up a small USB keyboard. Let's give it a try again. Indeed, 400 MHz, Intel Pentium 3. Quite some memory. And it doesn't recognize my small USB keyboard. There we go, turning it off and on again, got it further. Either my monitor is bad or the VGA output is bad, because it looks quite different than what's on the actual screen. Although the screen is quite broken, the colors look a lot better there. I can play with the different menus. Let's see what the self-test does. By the looks of it, this thing can test 10 gigabit per second network connections, which, well, in the era of a 400 MHz Pentium 3 would have been really fast. I see that the self-test has a failure. Well, the self-test found 5 errors, so besides this being some obscure test equipment, it's also not working. So I'm just going to take it apart, see if there are any goodies inside, see how an instrument like this is built, and I won't lose a good instrument. So this is the side of the instrument, with all the connectivity options to test the different connections. And you can see it indeed, it tests around 10 gigabit per second connections, so quite fast. For nowadays 10 gigabit is a decent speed, but back in the day when this instrument was made, must have been really top of the line. Those instruments like this are quite complicated. Now I have 2 optical connections, shielded to prevent dust. As you can see, they don't use the typical HP connectors, either because this instrument is newer, or it was made with components from other manufacturers and they can use their own standard. So let's see how we can get in. Took a bit of figuring out which screws to loosen, but now I managed to get the side panels off. So let's see what's underneath. So internally the instrument uses different cards that are slotted in. That's not uncommon for test equipment. So let's have a look what comes out. So this is some kind of digital board, which probably is not the most advanced. There are some heatsink chips, small subboard, very big multi-pin connectors, besides a few larger packages which may be relays. This is mostly just some digital electronics. Now the more exciting board, the one with the optics. So let's see how 10 gigabit communication looks like. Well, the fibers are routed to the back, and on here we only have 5 very big heat-sinked ICs and some other heat-sinked things on the side. Ooh, and here are a few shiny packages. Stick in the heatsink, and both fibers go into these packages. One will be the transmitter, the other one will be the receiver. So it's a 1550 nanometer laser. Let's see if we can open it up. Now I only see a few screws, so I'm not sure if this package will actually open up like this. Let's see if I can unmount it. The module is connected to the big PCB via some quite high density, I guess high frequency connector. And here we can actually see how the package should be opened. The fiber runs underneath the other module, so I'll loosen that one as well. On the side we can see that it's JDS Uniphase who made this unit. Both units actually. Now we can actually also look at the bottom of the PCB, and it's basically only filter capacitors. So if you compare these boards with the communication test set that I previously opened up, see it's a lot more populated with heat-sinked ICs and only just a few big heat-sinked ICs, and it's not a whole zoo of electronics. So nowadays I guess stuff is a lot more integrated, although nowadays this is still the Pentium 3 era. Now it looks like these are just FC connectors on both ends, so let's see if I can loosen it. And indeed, this is just an FC fiber. Unfortunately the coupling itself is something like riveted to the case, so I can't take it out. Let's see what's inside one of these laser modules. There you go. Well, this is interesting. There are 2 layers of PCBs. And it seems like this multi-pin connector goes to the bottom one, and there's this extra one on top. Well, this is interesting. This is actually the receiver, and if you look here you see sort of a butterfly package with a lot of different leads and a coaxial cable running out of it, and you'd almost think this is a laser diode because they also come in these like butterfly packages, but it's actually the receiver. So that's quite interesting. I would not expect a receiver to have so many pins off to the side. If you compare this to the older communication tester that I took apart, there was just a 2-pin photodiode right at the edge of a PCB where the signal was tapped off. Now if there's a really high speed photodiode in here, it will need some bias voltage, and perhaps there's already some amplification going on in here to amplify the optical signal. Now I don't know what else would be going on in there, and there's quite a lot of pins off to the side, so it might be interesting to open up this package. Otherwise, unless there's a datasheet available, I probably can't use it as is, because figuring out how this thing works just by the looks of it will be quite difficult. If you look at this smaller board, there's a microchip PIC on it and a Burr Brown chip, which is an AD-S7809U. I guess that's an AD converter. And the BB DUC7614E, I guess that's an DA converter. And the op amp here and the op amp there, several op amps. So perhaps this one is the some control logic for the analog part, since there's so many digital to analog and analog to digital parts. If we look inside here, we can see the coax cable runs here off to the side of the PCB and via a dedicated trace goes into this special package. So this must be where the high frequency stuff is happening. And after that you see some dedicated lines going off to this chip, and from there I would guess things go a lot more in the digital domain off to these buses. So to compare the two boards, this is the receiver board of the older communications tester, and this is the photodiode, and there on the side of the PCB are the two leads that just directly go onto the PCB, and here you have this whole specialized package, coax cable, high frequency traces. So that's quite different. So I couldn't find any datasheet for the receiver module, so I wanted to take it apart to see if I could reverse engineer it. Now with a hot air gun it didn't open up, so I went to the milling machine. Now looking inside, you can see that the fiber comes in, it's soldered down, I guess either as a strain relief or just aligning it, and it goes through a very thin ceramic PCB. On the other side of that PCB is what I think a very small photodiode. Of course, the smaller, the lower the capacitance, the faster. And that photodiode is directly connected to a very small IC via bond wires. Now it's really interesting. I guess I'm seeing a bare silicon wafer, or maybe not even silicon for these high speeds. But it also looks like I've broken a few of the bond wires. The milling process wasn't exactly gentle. But yeah, with such a complex chip inside, I don't think I have a chance of reverse engineering it. So it's nice to have a look inside, but I won't be able to use this unit. Let's open up the laser unit and see what's in there. Again, a warranty seal that I will be voiding. And here we again have a two-layer construction with the top PCB and the bottom PCB. There's a bit more going on. Actually here you can already see a description, optical modulator driver. Well, that's interesting. Let's see what we find here underneath. So that almost sounds like we have a dedicated modulator that's coming after a laser diode. Look at the PCB that come off. It's a lot of different op amps. Again, AD converter, another PIC microcontroller, digital to analog converter, quartz crystal. Here one of the SMD packages threw its lid open. This inductor broke off. Might still have been working good enough, but it's interesting to see something so broken so deep in the machine. So this is the laser diode where it all starts. This is a fairly standard butterfly package, and that fiber is routed around the module here. I guess this is where the fiber is fused. It's just a connection, I guess. And then that fiber is routed around and is inserted here into the gold part. And the gold part also has an RF connection to this thing, the optical modulator driver, which has several input voltages and an RF input. And I guess this is some kind of RF amplifier, and this in turn drives some kind of modulating technique that's in here. That's actually quite interesting. Let's see if I can take this a bit further apart. I undid all the screws. You can see it's soldered here. Not sure why. I'm trying to remove it straight back, and you can see here it unplugs from the driver. Interesting. You see indeed a JDS uniface. Here you see the description of the wires: bias, ground, DOC, input, output, RF signal. So this is the actual modulator. I might just mount it back in this case, since there's a rigid connection between the modulator and this RF module. So I think it's best to leave them connected, and then I'll screw this back in place. So I may have to reuse the package if I ever want to make use of this modulator. The datasheet of the laser of that butterfly package actually says it's very well suited to be used in combination with a modulator. The laser diode then provides a nice stable optical source, while the modulator actually puts the data onto the signal. So let's see how the rest of the boards look. So this is the clock generator. I guess this will mostly be a digital board. A lot of the same type of chips. I'd have to look up the datasheet what the chips are. But it's not a too exciting board. Backside will be mostly power stabilization and small stuff. And for a clock generator you expect mostly digital logic. And then the bottom board, labeled as processor, that will be our 400 MHz Pentium 3. And indeed 256 megabytes PC100 memory. And under this big heatsink must be the processor somewhere. I guess also the chipset is cooled. There are several ICs underneath here, it's hard to see. And the floppy drive in here. It's a fairly compact board. So this is pretty much industrial single board computer. And there we go. 108 megabyte compact flash. That must be the hard drive where the operating system resides on. Might be interesting to have a look at it. See if I can identify anything of what's running on here. And then we've reached the bottom of the machine. And all that's left is just to look at the very big backplane with lots of multi-pin connectors at it. But otherwise fairly empty. Now if we rotate the unit, I already took the other panel off. Here you can see just the power supply and I guess the speaker. But there is some space in between. This metal here and the backplane, they're not sitting back to back. So there might be a deeper level in here somewhere. Let's see what I can find. Let's first take the power supply out. So we have a lambda power supply with I guess 2 times 12 volt 4 amps and a 5.2 volt 10 amps. And over here we have 5 volt 20 amps and 3.3 volt 30 amps. And some smaller voltages. Some control signals. Some sensing lines actually. It's quite a beefy power supply. It seems I can just unplug everything from here. There we go, one power supply. It's a bit of a hefty unit. You can see a lot of capacitors in the back there. But since there are sense lines, then it gets more serious. That's not something you see in a regular PC. Now it looks like here's a panel that I might be able to take out actually. So I don't know if the whole casing will fall apart or if this just comes out easily. Let's give it a try. Now I wonder if this is the correct disassembly order, but it's a maze of panels and screws, so let's just give it a try. At this point I don't see what's stopping this panel from just popping out. They're not afraid to use a lot of screws. The back seems to be some kind of cast aluminum, so quite sturdy. There we go. Let's unplug the fans. I found out where the side panel that I was trying to remove was still bolted on, right here, around the corner. So it was bolted in these directions and this direction. So that's quite complicated. I wonder what the assembly procedure of this is. Let's see if it now comes out. Well, I've now screwed nearly every screw I can find, so if now it doesn't come apart, I really don't know how this thing is put together. So I finally got it pretty far apart, and the case was actually a somewhat unexpected construction for me. So this box in which the power supply was and this backplane board, they're actually, I think, part of the structure of the whole case, and alongside that are panels mounted, basically connecting the front and back part together. I think both of them are cast aluminum. So it's not like it's a case in which stuff is placed. It's sort of every panel together makes the case. The construction of this machine probably started with these two metal plates, then the two cast aluminum parts alongside of it, and then the panels around it. Now what's interesting to note is the thickness of the backplane PCB. If you look at the small PCB that I put on top, this is a regular PCB that I took out of the rest of the machine, and just compare the thickness to this huge backplane board. I don't know how many layers that PCB has, but it's a lot. I guess all these multi-pin connectors must be routed somehow, and if that also needs to be done without them interfering with each other, there may be extra ground planes or stuff like that in there, and then you end up with a lot of board layers. Also interesting is that on the backplane you see these colored plastic inserts that have slightly different shapes. Now that's probably because the boards have to be plugged in a specific position so that you can't mix them up. It's quite interesting. Of course the casing has all the connectors at specific locations, so you can't just swap them as it then won't fit in the case anymore. And by those 4 tiny screws, the front panel goes open and the handle comes loose. So if you carry the instrument by the handle, it's carried by 4 small screws, plus of course the big T20 screws that I removed. Just look at how this is very tightly shielded. A very fine grid. Only the above slots are for ventilation. The rest is just to have all the noise of the outside world that could be coming even from the display or anything else behind it, just to block it off. So really a neat RF shield. In fact, this cable is going through a slot, and that slot is just a plate that's screwed in and pushed to squeeze the slot as tiny as possible. So if you want to get the cable out, you have to loosen these screws, slide this backwards, or maybe even remove it, and then it might be able to come out. Actually, judging by the size, it may have to come out indeed completely. Here you can already see the warning for high voltage. That will be for the fluorescent tubes behind the display. And of course, high voltage can be quite noisy, so it's very good that this is on the other side of the shield. A 64-pin cable. Twisted pair to reduce interference, I guess. I think this is the biggest flat cable I've seen so far. 64 pins. Let's see if the panel wants to come loose. Now you can hear a lot of these fingers. Trying to make everything tight. Oh, maybe this one needs to go as well. And we find a sharp display in there. I guess this board distributes the signals to the display and to the rest of the front panel. And here's already the back of the front panel with all the keys. You can see that there's a lot of rubber here around the screen, but it didn't protect the screen from actually getting a hit. Considering the solid build construction of this device, I guess there must have been quite a collision that broke the display. And here we go, the keypad. That's it. So that's it. I really took the instrument apart from front to back, and it really fell apart because the case has this funny construction. So it's really an eccentric piece of kit, not something you regularly see in between test equipment. And I'm not sure if I can make anything useful of this case. I'll probably try to put it back together, see how far I get. In any case, thanks for watching, I hope you enjoyed, and I hope to catch you next time. And there we go, a case ready for the next project. So thank you all for watching, I hope you enjoyed, and I hope to catch you next time.